I've noticed on the internet I couldn't find any full proofs of the cofactor expansion theorem, so I thought I would put one up for my class and for anybody else who wants to see it. Let me start with the following. Let A be an n by n matrix. We define the determinant of A to equal the following. And hopefully you understand what this definition is. This is along the first column. Of course, the cofactor expansion theorem says that we can do this along any column or any row, and that's what I intend to prove. But for now, let me make sure that everybody understands what all the notation means, and I think the only thing we need is this one. Whenever I write this, this is the same as matrix A, but with row I removed and column J removed. So Aij is an n minus 1 by n minus 1 matrix. All right, before I state and prove the cofactor expansion theorem, let me write down the assumptions. These are things that can all be proven pretty easily. If E is an elementary, n by n matrix, then the determinant of EA equals the determinant of E times the determinant of A. Now, I'm not assuming that the product of determinants is the determinant of the products. I'm not making that assumption, but only for elementary matrices. There are three types of elementary matrices: the row swap matrices, then you have where you multiply a row by a scalar, and then you have row replacement. And anybody who is coming to this theorem probably knows all of these by now. All of the proofs of the three types of elementary matrices involve mathematical induction. It's not difficult to do. I can always throw up something if anybody who watches this would like me to. Second, the other thing we're going to make use of is that the determinant of the transpose equals the determinant of the matrix itself. And of course, that proof, once again, is a basic proof where you break down the matrix into elementary matrices. So a quick sketch of that situation is something like the following. For this here, you assume A is not invertible versus A is invertible. And when A is not invertible, you can end up writing it something like this. When A is not invertible, you can do this. And in each of these cases, each of the EI is an elementary matrix. Now, in the case where A is not invertible, then you can write it as a product of elementary matrices times an echelon matrix. And once you have that U is an echelon form, since A is not invertible, there are fewer than n pivots. So if you look at U is going to be this upper triangular matrix that's going to look something like the following. We may have a block, and then I may have skipped some blocks, and whatever, it may look something like this. Above it, I really don't care, but below it, you know that you got zeros. Once you get to this point, you know that the determinant of U equals 0 because we take the product of the diagonals. The reason why that product is 0 is because we have fewer than n pivots. That means as we go along this diagonal, some of them will be missing. That means some of these spots along the main diagonal will be 0. So you'll be taking a product of numbers, some of which are 0. So that is why you get that determinant to equal 0. And then when you look at the determinant of A, that will be the determinant of EP down to E1 of A. And now, using those assumptions that I made before about elementary matrices, you can do the following. You can peel off one elementary matrix at a time. And keep going. And I made a mistake here. That is going to be my U. You can't, I mean, I guess you can do something like that, but it's completely silly. So once I get to that, then I really don't care what these determinants of the E's will be. So I'll get the determinant of EP down to the determinant of E1 times the determinant of U, which we know equals 0. So in this case, the determinant of A is equal to 0. Since A is not invertible, neither is A transpose. So the determinant of A transpose also equals 0. All right, so we've got the situation for A transpose. Now, if A is invertible, then we're going to be able to write A as a product completely of elementary matrices like so. And then when you take a look at its determinant, I'll be able to peel those off one at a time. Fortunately, the determinant of an elementary matrix is the same as the determinant of that elementary matrix transpose. That's another assumption I should have probably put in, but I did not. So let's go ahead and put those in right now. Those are, of course, those are never the things that people have problems with. It's the proof in general. So I've got that. Now, one at a time, because I can only peel off elementary matrices one at a time. I can only reassemble them one at a time. It just so happens that when you take the transpose of an elementary matrix, you get an elementary matrix. So I can put these things back together one at a time because they're all elementary matrices. Now, what I'm going to do before I put them back together is I'm going to reverse the order, though, using the commutativity of the real numbers under multiplication. So I did that. Now, each of those E sub I transposes is an elementary matrix. So I can put this back together in that order, E1 transpose up to E sub P transpose. And let me put the transpose in the right spot. Now, of course, the transpose of a product is the product of the transposes in reverse order. So this is the determinant of EP down to E1 transpose. But now EP down to E1 is no different from A. So this is the determinant of A transpose. And so what we've shown is that the determinant of A transpose is the same as the determinant of A. So this is called the cofactor expansion theorem. And it goes like this. Let A be an n by n matrix. Then it simply says the determinant of A equals the sum I equals 1 to n, negative 1 to the I plus j, aij times the determinant of capital A sub ij. So this is along column J. So remember, the definition is along column 1. This says that we can do the determinant along column J. And of course, the second portion of this theorem says the following. Here, J goes from 1 to n, negative 1 to the I plus j, aij times the determinant of capital Aij, and that is along row I. Now remember, my definition is along column 1. So we're going to have to, in the proof, we're going to appeal to that. Because the determinant of A equals the determinant of A transpose, we can swap any two columns of A and get the negative of determinant A. So whenever you swap two columns, you can you'll get a negative sign in front of the determinant. We proved, at least in our class, and one of the things that's proven before you get to this theorem is that you can swap any two rows, and what it does is it changes the determinant by making it a negative. because the determinant of the transpose is the determinant of the matrix itself, I can now say that that's true for columns as well. So I can swap two columns and get the negative of the determinant. That's going to figure really bigly in here. Bigly. So let's take a look at what A might look like. In fact, do this. Consider the jth column of matrix A. So A equals, let me highlight it just in case we're going to need to speak of it. So I might do A11 up to AN1, and then we have A1J. I want to throw in here my AIJ. We may be making use of it. NJ. And then finally we end off this row A1N down to ANN. I just want column J highlighted for our purposes. Now what we're going to do is we swap columns J and J minus 1. That's what we do first. So we're going to get the the negative of the determinant, but this is what it looks like. Let's call it A prime for the time being. And so A11, nothing's affected except the jth column. But now I have A1J, AIJ, ANJ, but after that I have A1J minus 1, ANJ minus 1. I'm putting the comma there just so it doesn't get too complicated looking. And then after that, so far I have a negative attached to my determinant. So I guess we can keep track here. The determinant of A prime equals the negative of the determinant of A. Now swap columns J minus 1 and J minus 2. So what I'm going to do now is I'm leaving everything alone here, but this is in the J minus 1 column right now. I'm going to swap whatever is in the J minus 2 column with it. And here's what I get. Let's call it A double prime. I only need a couple of these till you get the idea. So here we'll go A11 up to AN1. But now we have A1 comma J, AIJ. I don't think I'm going to use the comma when it's so simple, so I'll just call it 1J, ANJ. It's when it's more complicated subscripts like this one. A1 comma J minus 2 down to AN comma J minus 2, A1 comma J minus 1, AN comma J minus 1. And then I think I need to put one more here so you can see that it's been taken out of this. A1 comma J plus 1, AN comma J plus 1, A1N, ANN. And this puts a negative in front of the determinant again, so I have determinant A double prime equals the positive of the determinant A because I removed the negative from last time. Well, what we're going to keep going until that original column J is in column 1. So you're going to keep going with swapping adjacent columns until you get all the way until the first column. So I'll have an A1J, AIJ, ANJ, and then after that I'll have an A11, AN1, and let me go at least to the places where I've plucked the column from. A1 comma J minus 1. After that is A1 comma J plus 1. So it's been removed essentially and gotten to the first column. Now to get there, it was already in column 1, so we did a total of J minus 1 column swaps. So what we have then is that the determinant of B equals -1 to the J minus 1 times the determinant of A. Now, take a look at the following. BI1 equals AIJ. Let's take a look. If I take row I out, so let's do that. I'm going to take row I out, and I'm going to take column 1 out. What do we have left over? We have the matrix A, right, except we are missing column J and row I. So now let's compare that with AIJ. Let me have AIJ. I think what I'll do, AIJ does this. So let me take these with me. So when I look at the two of these things, I go from A11 to A1N, but there's no column J. A11 to A1N, no column J. No row I, no row I. So you can see that these two things are the same thing. Furthermore, BI1 equals AIJ for all I. Let's see if that's true. BI1, so B11 is A1J, A1J. And you see, of course, it matches this column. This is the column, specifically the column that I moved into that location. Perfect. So expand the determinant of B along the first column. So the determinant of B equals the summation I equals 1 to n, -1 to the I plus 1, BI1 times the determinant of BI1. Now, based on what I said before, these things right here, I can just substitute them in. So we almost got what we want. However, don't forget that the determinant of B was also equal to -1 to the J minus 1 times the determinant of A. So the determinant of A equals -1 to the J minus 1 times the determinant of B, which equals -1 to the J minus 1 times the sum I equals 1 to n, negative 1 to the I plus 1 aij times the determinant of aij. Let me bring in the negative 1 to the j minus 1, and as you'll see, what it does is make the exponent perfect now. And that finishes the proof for column J. So we can expand along any column since the determinant of A equals the determinant of A transpose. We can also expand along any row. And that finishes the proof.